Hi. So in the last video, we covered about lemmatizing and stemming. That was the most important part for our entire pre-processing task. Now we will do some kind of analysis over here. In the previous video, in the previous few videos, we saw that there were the stop words which were dominating. Now, as we remove the stop words, we stemmed the sentences, we lemmatized the sentences. Now the plot would look something different. So if we try to plot the plot over here, we'll be having a whole different kind of plot. So over here we are seeing this, the instead of to, the, and all. So we are having some words which are conveying some kind of meaning, like father, murder, become, return, also, life, to, time, and all. So yeah, this is an indication that we have successfully stemmed, lemmatized, and removed the stop words. And now if you look at the count of them, so we will see that the one keyword is occurring more number of times, find is occurring next, kill is occurring next. So maybe, yeah, so there are few words which are occurring more than once or more than 1,000 times in this. So these are not the stop words, and in short, these are not the stop words. So that is a clear indication that our pre-processing tasks are perfectly done. Now we will do the encoding task over here. So if we just look at the list of books of unique, so that means we are not having, so basically we are having all the categorical variables, right? So if we just look at the genre if we just look at the genre of books, we are having this fantasy, science fiction, and all. We need to label them. We need to label these, right? Why we need to label? Because machines can understand only numerical terms. So we need to do some label encoding to this. So what we are doing is this function is doing the label encoding task. Over here we can see that this function is converting this is one books list, which is this list, and this is an encode list, which is just 0, 1, 2, 3, 4, 5, 6 numbers, and then we are zipping these two lists to make a dictionary. So this will make this kind of thing. So now what we need is we need to map wherever it's fantasy, we need to keep it 0. Wherever there is science fiction, we need to keep it as 1. Wherever crime fiction, we need to keep it as 2, like that. So what we'll be doing is books of genre is equals to books of genre.map of mapper. So this will be using, so this will map. So in the books of genre, the column, wherever there are fantasy, map it with 0. Wherever there is science fiction, map it with 1, like that. This entire statement is meaning. So if we just execute this, we are saying that now unique values are, instead of unique values being fantasy, science fiction, and all, the unique values are 0, 1, 2, 3, 4, 5. Now we'll look at the model building phase. So in model building, we have to convert the summary value into an count vectorizer, or the vector in a vector format. So for converting the sentence into vector format, that is basically the numerical representation, we'll be using this method known as count vectorizer. So in count vectorizer, we'll say max difference is equals to 0.90, min difference is equals to 2, max features will be 1000, and stop words will be using as English. If there are any kind of stop words, just remove those stop words. That is the meaning of this. And bag of word vectorizer is equals to count vec.fit transform books of summary, right? Count vec of fit underscore transform of book of summary. If I just execute this, it will return a sparse matrix for me over here of 3000 into 1000 dimension. Then we will as we all know that, as I said in the starting only, the summary we will be using it as training, and then testing for, and our dependent variable will be and our independent variable will be the genre, and the independent variable will be summary. So we are saying test is equals to books of summary, and we are applying train test split, so that the data gets split into test training and validation. So if we look, 2400 for training and 600 for validating. Now we will try to fit some algorithms on this. Now let's start off with multinomial NB, because this is very fast and it works very quickly on text data. So it is giving me an accuracy of 65%. Let's see out with random forest classifier. It will take a little bit time, and the reason why multinomial NB, that is multinomial naive Bayes, is working good is it will not understand the context behind the scenes. It will just see where it will work on basis of counting. Like basically these words are occurring more, so these words will get priority, and then these words will get some kind of distribution in the end. So in cases of text and everything, multinomial naive Bayes and Gaussian naive Bayes or linear models like support vectors also work good. But when it comes to random forest classifier and anything, it will not work good, because over here you can see this keyword named as sparse matrix. So in sparse matrix is a kind of matrix which will have a lot of zeros. So in random forest classifier, if when we are calculating the impurity or gain behind the scenes, as random forest classifier uses decision tree, behind the scenes impurity has been calculated, like this information like entropy or Gini. So when that is calculated, when it reaches a value of 0, that means the node is ended over there. There is no further node which is proceeding. So in decision tree or random forest, many of the nodes which are not so much of the information which is to be conveyed is not conveyed in the algorithm itself. So that is why these algorithms do not work well on this. Boosting algorithms can kind of work well, because boosting algorithms work on the main fundamental thing of boosting algorithms is they work on the previous iteration. They try to fix the errors which were there in the previous iteration. So that is the basic difference of boosting algorithms and ensemble algorithms. So while coming to support vectors and multinomial, these are all the linear models which will use some high dimensional data analysis, and will do a certain will work on distance parameter mostly. So in high dimensions, calculating distances like a Euclidean, Minkowski and all, it's very simple for these algorithms. So we saw that the accuracy scores are not good. So we will try to use some other vectorizer over here. Instead of count vectorizer, let's use some TF-IDF vectorizer. So now what we will be doing is we will be using TF-IDF vectorizer. So what we will be doing over here, first we'll use sklearn. From sklearn we'll import label encoder. So in order to give the mappings of this book genre, we'll import the label encoder. Actually this step is not required, but because this step is already done over here, that is we are already mapped, but it works fine even if you don't want to do. After all, the result will be the same only. Xtrain, ytrain, xtest, ytest. If you just try to do train test split on books of summary, which is our training, and y, which is our books of genre. So if we just do train test split on this, we'll get the training and validation data, and we see that, and then we'll be using this TF-IDF vectorizer over here. So TF-IDF vectorizer will take maximum difference of 0.8, maximum features will be 10,000, and then will fit underscore transform on xtrain and only transform on xtest. Will not use fit underscore transform on xtest or validation data, because understand a very simple difference between fit underscore transform and transform. The fit underscore transform will consider the label as well along with it, and with that it will use the distribution and it will fit it, right? Whereas transform is basically we want to check whether our validation data will perform great or not. As we have trained our model on training data, we need to check whether it is correctly validating on the validating data or not. So for that the reason we will not use fit for that. If we use fit for that, we have to consider the labels of those validation data as well. So that will not make any sense, because model will learn the entire thing at once. So basically we need to separate it into training and validating. So that is the reason why we will use fit underscore transform and transform. If we execute this, it will take a little bit time and it will return me the xtrain TF-IDF and xtest TF-IDF. So that will be a sparse matrix after all. So this is the support vector classifier which we are defining, and we are passing in we are passing the training data, and we are predicting on the testing validation data. This will take a little bit time, because support vector classifiers internally use a lot of computation. They will use the kernel trick, which is the kernel may be RBF, linear, polynomial, or many kernels are available in support vectors. So they will be using all those kind of kernels, and behind the scenes all the computation has been done. So over here SVC, so basically TF-IDF vectorizer gives I think so good results, because it is using some kind of mathematical formulas back of the scene. So we are seeing that it is giving 77.5% accuracy. If we are using multinomial NB, it is quick. As I said, that it works on counting logic. So here it is giving 78% accuracy. So we can see that there is a shift from this, there is a high shift from this count vectorizer, if we are using count vectorizer, we are just ending it up some 66%. But if we are using TF-IDF vectorizer, we are ending it up some 78% accuracy. So you have to always try and look for other methods, because by trying some other methods we can get some good results, as we saw over here. So in the next video we'll cover about the testing of those model, and then we'll look at, and then we'll try to integrate everything into the Flask